Good morning and welcome to Tech 240 on Wednesday, March 3rd. Today we're going to kind of switch gears from talking about generators to talking about motors. And we'll start by talking about DC motors for a few class sessions, and then we'll switch and talk about AC motors, because AC motors are just a little bit different than DC motors. But before we make that switch to talking about motors, I think it might be helpful to do a few more review problems on generators. So let's do that. I'm going to switch over to my document camera so we can do a couple of review problems on generators.
There we go. All right. So I think you can see all of this at the same time. The first problem says that we've got a coil of wire. It's in the shape of a circle and it has a radius of 10 centimeters. And the coil is passing through a magnetic field that changes from 0.7 Tesla to 0.2 Tesla in 0.05 seconds. And this time we measure the output voltage of the coil, the induced voltage in the coil, and we measure that it is 100 volts. So the unknown this time is how many turns of wire are in the coil. The second review question, there's only going to be two. The second of two review questions is we've got this generator as drawn here. And we've got the direction of rotation. It's rotating around in a clockwise direction as shown in red. And we've got the direction of the current flows caused by the induced voltage in the armature. But the one thing that we don't have here is the polarity of the magnetic field. So we don't know if this is north and this is south, or if this is north and this is south. But you can tell me if you apply, well, if you think about it, and I'll go over how to do it in just a second. But first, why don't you pause the video and take a couple minutes, take however long it takes you, to figure out these answers. Both of these problems would be pretty strong candidates for something very similar to this to appear on the next quiz or on the next exam. So go ahead and pause the video and see if you can figure these out. Okay, I will assume that you have paused the video and taken a few minutes to work these out. So I'm going to go through the answers. So in the first problem, we're given a description of what is obviously a generator because we have an output voltage, an induced output voltage. And we're also given a bunch of parameters about the size of the coil of wire, the armature, and we're given the change in the magnetic field, and we're given the change in time. So we have only one relationship, only one equation that talks about the relationship between the size of the coil of wire and the change in the magnetic field and the change in time and the induced voltage and the turns of wire. We only have one equation that could possibly be relevant here, and that is Faraday's law. So I'm going to switch over. We've got Faraday's law, and our equation for Faraday's law is this. It tells us the relationship between the induced voltage that we're measuring at the output and the number of turns in the armature and the change in magnetic flux, not field. I do see that as a pretty common error, is just putting magnetic field in here, but it's not the field. It's not just the field. It's the change in magnetic flux through the armature. Remember, we're talking about slicing through lines of magnetic flux. That's the only way you induce a voltage. So that's our term for change in magnetic flux. And it's the rate of slicing through those lines of magnetic flux. It's a rate, and so to make it a rate, we divide by delta T. So in this problem, we're given a whole bunch of stuff. So I like to just write down what we're given first. We're given that the induced voltage is 100 volts. We're given that the delta T was 0.05 seconds. That's how long it takes for it to go through a certain change in magnetic field strength. And from the change in magnetic field strength and the area, we can get the change in magnetic flux. So we know delta T and we know E induced. We're trying to find N because the question is how many turns of wire are in the armature. So to solve this, we got to know everything else besides N, and then we'll rearrange this equation for N and plug everything else in and solve for N. So we got to find the change in magnetic flux. It doesn't tell us what it is. It only tells us the change in the magnetic field strength. And we can also find the area because it tells us what the radius is. So we had this relationship for the change in magnetic flux. Remember, the change in magnetic flux is phi2 minus phi1, and we can rearrange that. We can rearrange that to show that that is equal to the area times the quantity B2 minus B1. That's the magnetic field strength, or the average magnetic field in the armature that it's going to minus what it was originally. That's the change in the magnetic field strength. So what it's changing to is 0.2 Tesla, and what it's changing from, that's B1, that was 0.7 Tesla. And before we plug that in, we got to calculate the area. It doesn't tell us the area, it tells us what the radius is though. And it also says it's a circle. So the area is pi r squared. So we plug in the radius. It tells us it was 10 centimeters, which is 0.1 meters. Be careful when you're doing these problems because sometimes the problem might give you the radius, sometimes it might give you the diameter. Sometimes the armature is going to be a circle, sometimes it's going to be a square or a rectangle. So pay attention and be careful when you're calculating the area. But here's our equation for the area of a circle. 0.1 meters quantity squared times pi gives us 0.0314 meters squared. And we know B2 and B1, that's what the magnetic field is changing to. That's what it's changing from. So plug all that in and we can get our change in magnetic flux. That's the area from there. And this is the change in magnetic field strength. So plug all that in. And remember, we have an equation, the magnetic flux, or the change in magnetic flux, is equal to the area times the change in magnetic field. Phi is equal to BA. Phi equals BA. So from that, we get our change in magnetic flux, and we solve this, and we get that the change in magnetic flux is negative 0.0157 Webers. If you take a meter squared times a Tesla, you get a Weber. That's the unit of magnetic flux. So now we've got everything except in. So now in our original equation, we can rearrange this equation for in. That's what I'm going to do next without plugging anything in because that just complicates things. So the next thing I do is rearrange Faraday's law up here for in. And I do that by taking both sides multiplied by -1 to get rid of that. And then I take both sides times delta t to get rid of that over here, and that brings it over here. And then I divide both sides by delta phi, change in magnetic flux, to get rid of that over here, and that brings it in the denominator over here. So that's what I end up with. Now, I have the number of turns in the armature is equal to negative E induced times delta t divided by the change in magnetic flux. And I know all of these things now. So I plug them in, and I get negative 100 volts times 0.05 seconds divided by negative 0.0157 Webers. Keep all those negative signs, don't lose those negative signs. And when I plug that into my calculator, then I get about 318 turns. You can't really have a fraction of a turn, not really. So just round. There's definitely some rounding error, in here. In some of these measurements, I'm sure there's rounding error. So just round to the nearest number of turns, and you'll see that it's about 318 turns, which is probably fairly realistic to a real world generator. Okay, that was number one. And then number two, we know this is a generator because it tells us it is. And so we know that we have a relationship between the magnetic field polarity and the direction of current flow due to the induced voltage and the direction of motion. We have that relationship via the right-hand rule for generators. So we're trying to find the polarity of the field given the direction of motion or rotation and the direction of the current flow as caused by the induced voltage. So this is definitely a right-hand rule for generators problem. We've got to match up the two that we're given in order to find the third. And the two that we're given, we know the direction of motion. Let's go ahead and write those in. The direction of motion, if this armature is rotating clockwise like this, then at this point in time, this side of the armature is going up, and this side of the armature is going down. They have to be if this thing is rotating clockwise like it says it is. So now I like to apply the right-hand rule for generators to both sides. First one, then the other, just to check that they are consistent, not the same, but consistent. Because obviously both sides should be experiencing the same magnetic field. Either this is north and this is south for both of them, or vice versa for both of them. They're both in the same magnetic field. So let's apply it. It really doesn't matter. Let's apply which order. Let's apply it on the left side of the armature first. So I know that my thumb for motion has got to be up, and I know that the current is coming out of the page. All right, so I need to apply my right-hand rule such that the current is coming out of the page, and the thumb is, and the current is the second through fourth fingers, and the motion, or the thumb, is up. So the only way that works is if it's like this. Our second through fourth fingers are coming out of the page. Our thumb, for the motion of the wire, is going up toward the top of the page, and the field, which is the first finger, is going from right to left, pointing from right to left. So maybe what I'll do for now, I'm pretty sure that this side is the north and this is south. I'm going to write it in pencil for right now, and then I'm going to apply it to this side, and I should get the exact same thing because they're both in the same magnetic field, and so I'll check it by applying the right-hand rule to this side. So for this side, I need to use my right hand, and I need my thumb for motion to be going down, and I need my second through fourth fingers to be pointing into the page for the current. All right, so the only way I can get that is by going like this, right? Where the motion, that's for my thumb, is going down towards the bottom of the page, and the current flow, that's the blue, is going into the page. And so once again, my first finger is going from right to left, and that indicates that the magnetic field is going from right to left. And it goes from north to south, so therefore the north is on the right and the south is on the left. So I just confirmed that, so now I can write it in marker. North on the right and south on the left. All right, so I think that's enough review for today. If you have any questions about these, then feel free to shoot me an email or come to the live Zoom session. I'll be happy to talk through any of this stuff. We can talk more about it.
All right, that's going to wrap it up for this video. In the next video, we're going to start talking about motors. So there are some similar principles between generators and motors. So they're not totally different. And I think you'll see that as we start talking about it in the next video. So I'll see you in the next video.